Welcome back to The Explainer, everyone. So, have you ever actually stopped to wonder what exactly makes up the number line? I mean, really makes it up. Today, we're zooming way in to look closely at the very fabric of our mathematical universe. We'll be moving from those simple, friendly fractions you're already super familiar with, straight into the mind-bending, infinite numbers that literally complete our reality. It's like a giant puzzle, and we're putting all the pieces together.
Here's our roadmap for this explainer. First, the irrational mystery, then pi and infinite series, followed by decimals and magic. After that, we'll build the real numbers, solve some key questions, and finally wrap up with a student quiz just for you. Let's get right to it.
Okay, so before we really get going, I want you to consider a mystery. A mystery that honestly shocked ancient mathematicians when they suddenly realized their beautiful, perfect number line actually had holes in it. Imagine you just draw a simple square on the ground, right? And each side is exactly 1 unit long. Thanks to the Pythagorean theorem, we know the diagonal of that square is the square root of 2. Easy enough. But when early mathematicians tried to write down that length as a simple fraction, they hit a massive, massive wall. They realized that entire classes of numbers were just missing from their standard toolkit. No way, right? But it's true.
Section 1. The irrational number mystery.
So let's start by filling those holes and looking at our first major building block. The absolutely crucial thing here is understanding the stark difference between two fundamental types of numbers. Rational numbers? Those are your friendly everyday fractions. You know, any number that can be neatly packed into the form p over q, where p and q are integers. But irrational numbers, well, they're the rebels. They are the wild, endless, chaotic decimals that absolutely refuse to fit into those simple fraction boxes. The square root of 2 is arguably the most famous example of an irrational number, and the way they originally proved it couldn't be a fraction is, honestly, one of the most beautiful pieces of logic in all of history.
Flashback to around 400 BCE, a mathematician named Hippasus used a technique called proof by contradiction to literally trap the square root of 2. It's like a logic puzzle. Here's how he did it. Step 1. He said, all right, let's just assume it is a simple fraction, p over q, in its absolute simplest form, no common factors whatsoever. Step 2, square both sides. Then step 3, basic algebra shows us that p squared is a multiple of 2, which means p has to be an even number. Okay, fine, but step 4 is the trap. If we substitute that even number back in, we find out that q must also be an even number, and boom, step 5, contradiction. We assumed right at the start they shared no factors, but if they're both even, they obviously share a factor of 2.
And because our initial assumption just blew up and created a massive contradiction, that assumption must be totally wrong. The square root of 2 literally must be irrational. It just cannot be written as a fraction. This single, elegant realization completely changed mathematics forever, because it proved, without a doubt, that some quantities in our universe just defy simple ratios.
Section 2, pi and infinite series.
Now, let's see how this exact same logic builds into one of the most famous numbers of all time. For centuries, absolutely brilliant minds, like the great Indian mathematician Aryabhata, really struggled to pin down pi, the ratio of a circle's circumference to its diameter. Back in 499 CE, he came up with an incredibly accurate approximation, 3927 over 1250, which gives us 3.1416. Pretty close, but, and this is key, he explicitly stated this was only a sana, an approximation. He intuitively recognized the pi, much like our friend the square root of 2, was an irrational rebel that couldn't ever be perfectly captured by just one simple fraction.
Actually, it wasn't until Madhava in the 14th century, the guy who launched the amazing Kerala School of Mathematics, that we finally unlocked this profound formula. He proved that you actually need an infinite sum to express this irrational marvel perfectly. Since pi is irrational, no finite stopping sequence of fractions will ever do the trick. Madhava discovered that pi equals 4 times an infinite alternating series. Look at this, 1 minus a third plus a fifth minus a seventh, and so on, forever. And adding an infinite number of terms just means finding the precise value that we get closer and closer to as we keep adding. It's just a breathtaking bridge between the finite and the infinite.
Section 3, decimals and cyclic magic.
Okay, so how do we spot these different types of numbers in the wild? Well, rational and irrational numbers look very, very different when we write them out as decimals. When you divide a rational number, one of those friendly fractions, it's always going to do one of two things. It will either cleanly stop or it will loop infinitely in a totally predictable pattern. For instance, 3 divided by 8 terminates neatly right at 0.375. Done. But 5 divided by 11? That gives you 0.454545 repeating forever. Why? Because in any division problem, there are only so many possible remainders. Eventually, a remainder has to pop up a second time. And the very second it does, the decimal starts looping. But irrational numbers? They never terminate and they never repeat. They are just pure, unpredictable chaos.
Now, I want to show you something that is just pure math magic, the cyclic pattern of 1/7. If you calculate the decimal for 1/7, you get this repeating block, 142857. Now take that block and multiply it by 2. You get 285714. Multiply it by 3, you get 428571. Do you see it? The exact same 6 digits never change. They just rotate their starting position in a continuous cyclic circle as you multiply them. It's wild. And this beautiful hidden internal structure, that is the absolute hallmark of a rational number.
Section 4. Building the real numbers.
So now that we have our repeating rationals on one side and our endless irrationals on the other, let's smash them together and look at the big picture. Every single length, every temperature, every physical measurement in the entire known universe has a permanent home on this newly completed real number line. You see, the rational numbers create this really dense web, but they still leave tiny microscopic gaps. By pouring the irrational numbers into those gaps, we finally create a solid, continuous, unbroken line. Literally the whole shebang. There are no more holes.
You can think of the rational side almost like a set of nesting dolls. The natural numbers you count with, 1, 2, 3, are neatly housed inside the negative and positive integers. And then those are housed inside the rational fractions. Then, on the complete opposite side, totally separate, are the irrational numbers, hanging out with pi and the square root of 2. But united? Together they create the complete master map of the real numbers.
Section 5. Solving key questions.
All right, we've mastered the theory, so let's shift gears and actively test out our new tools. I'm going to throw a number at you, and I want you to mentally categorize it for me. Okay, first up, is the square root of 81 rational or irrational? Think carefully about what it actually equals before you lock in your answer. Don't let that square root symbol trick you. And the answer is rational, because the square root of 81 simplifies perfectly to exactly 9, and 9 can easily be written as the simple fraction 9/1. So, pro tip here, always simplify first. If the root is a perfect square, it just hops right over the fence into the rational bucket.
Okay, let's try another one. Classify the number 0.33333 going on forever. Rational or irrational? Take a close look at this decimal expansion. Does it stop? Does it repeat? Or is it pure chaos? I mean, it goes on infinitely, which might totally make you think it's a wild, unpredictable, irrational number. But it is rational. Even though it genuinely goes on forever, it's a perfectly predictable, repeating decimal. Remember the rule? If it has a repeating loop, it belongs with the rationals. Irrational numbers never, ever repeat. Because this is just a very tidy, infinite loop of 3s, we can easily pack the whole thing up into the fraction 1/3.
Section 6. Your turn for a student quiz.
All right, I'm handing the baton straight over to you for a rapid-fire quiz to really cement everything we've covered today. Look at this decimal, 0.12345, 12345, and so on. Rational or irrational? Look really closely for a repeating block. You should spot pretty quickly that the sequence 12345 just repeats over and over again. And because it's an infinite but looping sequence, you now know absolutely without a doubt that this is a rational number. You could even convert it into a fraction using some clever algebra.
Speaking of clever algebra, I'm going to leave you with one final, mind-bending puzzle to chew on. Prove that in the world of real numbers, 0.999 repeating is magically, mathematically identical to the number 1. No way, right? Most people guess it's just slightly less than 1, but they are absolutely wrong. Try this trick. Let x equal 0.999 repeating. Multiply both sides of your equation by 10, and then subtract your original x equation from the new one. Try it out on paper. You will be amazed at the perfectly whole number that drops right out. Well, thank you so much for joining me on this journey across the unbroken number line. Keep questioning, keep calculating, and I'll catch you in the next explainer.